Okay, so today we're going to go over Euler's approximation method. Um, this is a really cool method of approximating what would be your solution, and this is actually noted in the movie Hidden Figures. This is kind of one of the big key moments in there. So it's kind of cool that you'll be learning something that was used by scientists or a rocket scientist to send somebody up into space and around the moon. So okay, anyway, so Euler's method. We're going to use the Euler's method to approximate the value of the function at a point. Okay, so that's what we're going to do. Um, so I just want to kind of get into it. Here is your formula, and this is what you're going to use. Okay, so you have to memorize it. It's not really that bad, but what you're going to do is you're going to take, to evaluate what a particular x value is, you're just going to take, and that's going to be equal to whatever the x value was at the prior spot times the step, and we'll talk about what the step is. Okay, and then yn of n minus 1, y of n minus 1, you're going to find that by taking it. So y of n, you're going to go and you're going to take the previous y value, and to that you're going to add on the step times this f of x n minus 1, y of n minus 1. And all that is it's the slope at the prior spot. Okay, so what all does this mean? Okay, so you have this curve, and we basically want to approximate what this curve is. So what we're going to do is we're going to go to this spot, and then you're going to go out some increment, which would be h, and you're going to go forward that much, but you're going to go forward along where the tangent line would be. So if you actually took the derivative at that spot, there would be the tangent line, and all you're going to do is you're going to continue to go up until you get to this x or this h value, and then you're going to stop and you're going to make your point. And when you make your point, then it's going to be x1, y1, okay, which gives you this picture down here. And then you're just going to repeat the process. Okay, so once again, you have this point right here, and you're going to go along at the slope, and so it's going to go like this, okay, something like this. You're going to go forward some h value again, and so you're going to end up getting this picture, and then we're repeat the process and get this picture again. Now you notice, I mean, this isn't perfect, but it does give a nice approximation for what the curve would be. Now, um, where do these formulas come from? Okay, so where do these formulas come from? So what we're going to do is the x naught, y naught, that would be given. Okay, that would be the initial point. The initial point would be given right here. And my goal is to come up with what would be the next one. So what I'm going to do is I'm going to draw a right triangle in here, like this. Now I've already talked about what this distance is. It's h. And so easy enough, if this is x naught, and I want to go over here, which would be the x1 value, I just have to take x naught and add h to it to get to x1. So this is going to be, the x value here is going to be x naught plus h. Okay, and that's pretty easy. Okay, that's all this is doing, is it's going to the prior x value and it's adding on h. Okay, so that's going to be really easy. So we'll go ahead and we'll fill in this. So x1 is going to be x naught plus h. Okay, going down here, we have x2. x2 is going to be equal to the prior x value plus that step. And then x3 is just going to be simply equal to the prior x value plus that step. Okay, so that's the easiest one by far. Now the harder portion is how you're going to figure out what this is right here. How are you going to figure out what that distance is here? Now the distance from there to there is the same distance as from there to there. So from here to there, that distance is y naught. All I need to do is figure out what this is right here, and I'm going to add them together. So I'm going to call that delta y because it's some amount that it's changing. So what I know then is my y1 value is going to be equal to the prior y value plus some delta y. Okay, now what in the world is that? I don't know exactly what it is, but here's what I do know. I know that it's going up at a slope of f of xy. That's what I know. I know it's going to go up with the slope of that. So I know the slope is equal to f of x, y. But this line, I can also calculate the slope by just doing rise over run. So it rises delta y, and it runs, well, h. And that's what delta x, y is equal to. So what am I trying to do here? I'm trying to figure out this equation right here, where this equation came from. And we've determined that y1 is going to be equal to y0 plus some delta y. But what is delta y? So if you go over here, delta y is equal to h times f of x, y. So you plug this in, and you have y1 is equal to y0 plus delta y, which is h f of x, y. Okay, and that's where that formula comes from. And this is actually, so I should restate this. Going back up here, the slope of this line is actually x naught, y naught. So these are all knots. Okay, which then gives us basically this formula. Okay, so let's go through and we'll practice this a little bit. So I have y1. Y1 is going to be equal to, you go to the prior y value, plus you add on the incremental step h, times you multiply it by the derivative at the prior spot. So you have x naught, y naught. Okay, pretty simple. Okay, so going down here, so y2 is, you go to the prior y value, plus you add on the step, times the derivative or the slope at the prior spot, x1, y1. Okay, and then the last one here, so y3 is going to be y2 plus h times f of x2, y2. Okay, you should actually be really happy when you see this question on the exam. It's pretty straightforward. You just have to know the formula, but it's a bit laborious. You have to kind of work through it a little bit. It can be tedious at times, but it really is pretty nice. Okay, so let's go ahead and do an example here. Okay, so we're going to approximate the solution to the differential equation y prime is equal to x minus y, passing through the point 0, 1. So this is where it's going to start at. So this is my x naught, y naught value. Okay, use a step of h is equal to 0.1. Okay, now it doesn't really give us a question here, but I know I'm going to go up to y or to y3 or x3. So let's go ahead and fill these in. So x1 is equal to x naught plus h. X naught, like we said before, is 0. So if 0 plus a step of 0.1, so this is equal to 0.1. Okay, pretty simple. And then x2 is going to be equal to x1. x1 is 0.1 plus the step of 0.1, which is going to give you 0.2. And then the last one, you have x2 plus h. So this is going to be 0.2 plus 0.1, which is going to be 0.3. Okay. Now, normally this question, and it wasn't stated here, normally this question will actually state find y an approximation for y of 0.3. Okay, that's what it will ask. And so you know that this is where you start, this is where you have to go to. Okay, so right now we're trying to figure out y 0.3 is, and we're going to do it by utilizing this. Okay, so how do we do this? Okay, so the y values, once again, you go to the prior y value, which start off as 1, plus you want to add on the step, so 0.1, but now you're going to take it times the derivative at the prior location. Okay, so up here's the derivative. That's what our f of x, y is equal to. So if I go to the prior point and I plug this in here, I have f of 0, 1 is equal to 0 minus 1, which gives you negative 1. So this is going to then be multiplied by negative 1. So you have 1 minus 0.1, and that's going to give you negative, or sorry, 0.9. Okay, and then we repeat the process. So you go to the prior y value, 0.9, plus you're going to add on this step, so 0.1, and then times the derivative at the prior location. With the prior location, I have x1, y1, and that's going to be equal to x1 is 0.1, y1 is 0.9, so I need to evaluate f of 0.1, comma 0.9 is equal to, well, it's 0.1 minus 0.9, and so that's going to give you negative 0.8. So this is going to be negative 0.8. So that's 0.9 minus 0.08, which is going to give you 0.82. Okay, and then one more step here. So once again, you go to, so my x2, y2 is going to be given as 0.2, comma 0.82. Okay, and then I continue. So y3 is going to take the prior y value, 0.82, plus the step of 0.1, okay, times the slope at the prior location. So I have to calculate what f of 0.2, comma, 0.82 is equal to. So that's going to be 0.2 minus 0.82, which is going to be negative 0.62. Okay, and then I just have to continue the process. So this is going to be negative 0.62. So this is going to be 0.82 minus 0.062, which is equal to, so this is a little bit hard to do in your head, but so 0.758. Okay, so my approximation for y of 0.3, it's about equal to 0.758. And remember, on the BC exam, you have to go 3 digits past the decimal. So this is your answer. Okay. So I'm going to change this a little bit. I think this is actually meant to be something else. I'm going to change this to y prime plus y plus 1. Okay. So we're going to go through and I want to approximate this with going steps of this. So what I'm going to have, and this is how I usually do it. I don't usually do it this format. I usually just write this out, x naught, y naught. So I know this is going to be equal to the initial point, which is 0, 1. So 0, 1. And then I have x1, y1, which is going to be equal to, the step is 0.1. So 0.1, comma, I'm going to leave that open for right now. x2, y2 is going to be equal to 0.2. x3, y3 is going to be equal to 0.3. You have x4, y4, and that's going to be equal to 0.4. I still have to put in the y values. And then x5, y5, that's going to be equal to 0.5. Okay? So I just need to calculate what this is going to be. So remember, we go to the prior y location, which is 1, plus you're going to add on the step of 0.1, and then times the derivative at the prior location. So I have y prime is equal to y plus 1. So in the first case, you have y prime, and you're plugging in the 0.01, is just going to be equal to, well, that's just 1 plus 1, which gives you 2. Okay, so this is going to be 2. So this is going to be equal to 0.1, comma, and they have 1 plus 0.2 is 1.2. Okay, the next one. Okay, so you go to the prior y location, which is 1.2, plus you're going to add on the step of 0.1 times the derivative at the prior location. So I have y prime of 0.1, comma 1.2 is equal to 1.2 plus 1, which gives you 2.2. This would be 2.2. So it's equal to 0.2. Okay, and then you have 1.2, and this is 0.22. So this would be, what, 1.42. Okay? Repeat the process. See, this is why I mean it's laborious. Now, typically it doesn't ask you to do this. You don't have to go through and do all these steps. It usually gives you like 2 to 3 steps at the most, usually 2. Okay, so we're going to go to the prior y location. So we have 1.42 plus you're going to add on this step, and then you're going to multiply it by the derivative of the prior location. So we have y prime is 1, comma, I'm sorry, 0.2, because the prior location is right here, comma, 1.42, which is going to be 1.42 plus 1, which gives you 2.42. This will be 2.42. Okay, now I'm going to really start using a calculator here to ensure that I'm not making a mistake. So 0.1 times 2.42, you know, is going to be 0.242. And you add it to here. So I have 1.662. Okay. Maybe we should stop. Maybe we should just change this to 0.3. I think at this time it's just like redundant to the process. So my answer, y of 0.3 is going to be approximately equal to 1.662. Okay? Okay, next example. Oh, that's it. Okay? So your homework for this section is out of your book, page 523, 16, 17, 18, and 19. Okay? And that was Euler's approximation. Okay, thank you.